Hi, my name's Eric.
And my name is Brian. We are both assistant professors at the University of Toledo in Toledo, Ohio. We're going to discuss two courses we have created and developed for the University of Toledo. First is the Foundations of Art Studio Technology course, which we will refer to as FAST, which has recently become a required foundations course for our department. Additionally, it should be noted that the course is also a Gen Ed course, which brings students from across many disciplines into this class. The other, Biodesign, is an advanced transdisciplinary course that brings students from across the university into a studio design-based class. These two courses have made a great impact of how our students engage with the tools for creating and the deeper thinking and analysis required for innovative design.
We created FAST at the University of Toledo in 2016 to fill a need we saw within the students and our program. We noticed that for our students, the traditional high school shop class had been replaced with computers for them to work virtually, and CNC tools like 3D printers, which were usually operated by instructors or staff. We saw on many occasions that incoming students lacked the understanding of the limits or possibilities of these tools since they had used them only indirectly. Our solution to this issue was the creation of the FAST class, which allows students to safely encounter, access, and learn to use nearly every piece of technology in our department in the short time span of only a semester. This experience grants students an agency and a working knowledge of tools so that they can be more productive throughout the rest of their courses at the University of Toledo. This is paramount as we also recognized that tools in our department were being sporadically taught throughout their 4 years, and we wanted them to have a foundation at the beginning so that they could begin to master these tools sooner and then start to subvert them. The tools included in the course are presented sequentially, starting with hand tools, then power tools, welders, wide format inkjet printers and plotters, to CNC routers and CAD software and 3D printers. We build off the simple tools and we teach students how these tools are interrelated as we move to the more advanced tools. Additionally, as our students begin to understand physical tool use, they are also engaging with readings from Noe, Crawford, and Storney that derive from a Heideggerian philosophy of tools. This is significant as it helps students to begin to develop a strong foundation in the history and philosophical usage of tools. The course's ability to teach students the usage of this wide range of equipment and the understanding of that equipment's interrelatedness comes down to a principle we use with each tool, unshrouding an invisible complexity. What we mean by this is that in addition to physically taking the covers off of equipment, we show the students the systems by which all tools are related and therefore can be understood. To help you understand this process, we're going to describe how we teach the laser engraver in our course as an example. First, students enter the room and they see that the laser has all of its shields removed. We then ask them to identify what they can. At this point, they've already learned hand tools, woodshop single motor tools, and inkjet printers, so they're aware of at least some of those components. When they can't identify a part, we ask them to figure out what kind of simple tool it is. Is it a lever, a pulley, an inclined plane? And then build the machine back up from that knowledge. Ultimately, they see that the laser engraver is just a cheap box holding a very expensive component, the laser tube, that's all controlled with software which they learn to understand and interact with on the computer. The next step is to put the machine back together, and we demonstrate the regular use of the machine, pointing out areas of safety concern for the student and the machine along the way. We then ask a student to repeat the process and follow up with a review as a class. Importantly, during this review, we're asking students to consider the philosophical constructs surrounding this tool, its place in a relationship to the other tools that we've taught, and more importantly, what this tool could be used for that it's not advertised to do. How can students think about pushing these prescribed uses into new areas for design? These prompts get the students thinking about their relationship to the tools and the tool's relationship to the possibilities of their future work. We also want to note that we do not consider the list of tools taught by this course to be sacrosanct either. In fact, the unshrouding of these invisible complexities can be applied to any tool or system, and we're constantly reconsidering which tools are necessary to teach for the education of good designers. To that end, we've successfully been funded by a grant to create a physical space in our department for the FAST course. This will allow us to continue to build on the relationships between the tools we teach, the philosophical connections between tools and users. Our lab, which is under construction right now, will allow us to not only teach FAST effectively in a single space, which we weren't able to do before, but also other foundation courses. On a community level, it will serve as a hub for the university in the creation of work that's fully informed on a philosophical and technical level. And finally, we'll use this space to teach advanced classes such as biodesign.
The second course that Eric and I developed and created for our department is the biodesign course. The Biodesign Challenge is an international organization that is connected to many universities nationally and internationally. The Biodesign Challenge organization seeks to create a community of collaborators among artists, designers, and biologists to seed first-generation bioengineers and build meaningful public dialogue about biotech and its uses. What spoke to us about this organization and what ultimately inspired us to create a university course was the opportunity to create an environment where our art and design students could collaborate in transdisciplinary teams. Each university involved with the Biodesign Challenge organization creates their courses differently, with more or less the same final goals, which is a yearly international summit and competition in New York. For us, we wanted to use this opportunity to create a more substantial course that made a greater impact for the wider range of students at our university long term. First, as I mentioned, the course brings together students from a wide range of disciplines. For us, it includes art and design students, earth and environmental studies, bioengineering, civil and environmental engineering, and life biology. This is the first course at our university that is able to work with this many disciplines at once in a classroom setting. Second, we wanted to construct a course that allows students to examine important components like system thinking and examining educational constructs. At its core, we built the biodesign course for students to engage and participate in the following. 1, students begin to reconsider the scientific method of observation, hypothesis, experiment, result, to more of a design thinking method, such as understand, to empathize, to define a problem, explore, to ideate, and prototype potential solutions, and finally materialize, or implementation. What is the impact of implementing a potential design solution, and what will it take to produce that solution? We call this the final mile. 2, engage students into system thinking through group critiques. We encourage students to see the overall complex structures, patterns, and cycle of their problems and potential solutions. Number 3, students engage in transdisciplinary readings, where students further unshroud complex systems and recognize similarities between systems. Some reading examples are Envisioning Information, Complexity, A Guided Tour, Thinking in Systems, Biomimicry, Donut Economics, and Outliers, to name a few. We also push students to recognize and examine their own discipline's educational system and structure, and in turn lay out the potential that resides in transdisciplinary learning and creating. Students begin to see how their specific discipline's education is technical and how they are taught and trained to look at the world through their discipline's lens. Each student, in a sense, begin to see themselves as part of a system that creates an expert in their field. They also begin to see how their discipline trains them to solve problems in a very specific way. As a class, we explore how these experts are trained to draw boxes around human problems and transform them into technical problems. Students soon see how this can contribute to misassessments and how things like context, history, and politics are often hidden or disregarded. we show students how transdisciplinary group learning addresses problems differently. From a multi-student expert lens system, student groups are able to assess problems in a wider and more comprehensive view, which ultimately sheds light on potential hidden or educationally biased aspects, and in turn creates more innovative and potentially greater sustainable solutions. To give you an example of how the course operates, we begin with an initial workshop, the first day of class, where students demonstrate their ability to listen, translate, and communicate information from peer to peer. The results in this workshop inform teams grouping and help students to recognize the importance of communication, translation, and translation of that communication. From there, student teams are not tasked with an existing known problem. Like in most of our senior design and engineering capstones, groups are given a problem by a client. But rather, our teams must immediately search for a problem to solve on their own, and to communicate their understanding of the scope of these problems continually to their instructors and to visiting experts from a wide range of disciplines. Students participate through multiple critiques throughout the semester, where they must respond to A, their understanding of a problem, B, their proposed solution, and C, the verbal and visual communication used to present their problem and solution. This course is critique heavy, where we invite leaders from the university and the community to help students understand broader issues. Teams revise and reiterate their design many times over the semester. Throughout this process, team members change tasks as necessary between research, design, and production, and hand these tasks off between those of different disciplines as the workload changes. As the semester and team projects move forward, an important feature of the course takes place. Students from design disciplines begin to grasp a deeper understanding of the science, and the students from science discipline begin to grasp the deeper understanding of design and visual information. The coalescence of these two produce a more developed visualization of the data and the prototype designs the teams are developing. There are times when teams run into dead ends and recognize disappointing results from their research and prototypes. To prevent complacency or distraction from their goals, teams are given directives that throw their project into a more chaotic state, which can enhance their creative productivity. Our goal is to break up the often predictable linear thinking and catapult them instead into a more creative and chaotic state, which in turn create new lenses by which to examine their research.
The contributions that FAST and Biodesign Challenge make to a curriculum individually are notable, but we think there's something unique and worth further examination that comes from the combination of these courses in a student's career at the University of Toledo. The three main contributions these classes make when run in tandem have to do with the implementation of tools for design education, the dissonance of the real world, and relationships between technologies. First, let's talk about current methods for teaching design, such as design thinking. We think that while this process does yield helpful results for students and companies, tacking this paradigm onto existing courses without a thorough rethinking of every decision that course makes can be problematic. To see what we mean, consider this. When a student is given the instructions to use design thinking, they most likely already have the tools to think broadly and ideate and to communicate with stakeholders. But in our experience, when students begin the implementation and prototyping phases of a project, they're limited by their understanding of how to work with physical and virtual tools, which generally only occurs after years spent working with other more seasoned designers in the field. The FAST and Biodesign courses grant students an agency over a wide range of tools and materials, and an understanding of the processes necessary to enshroud invisible complexities. This gives students the ability to create prototypes through techniques and materials not available to other students without this education. This knowledge even has consequences for the ideation stage of the design process, as students who have an extensive knowledge of tools and materials will be able to imagine solutions to design problems in a broader way, and this design exploration is extended even further when a student is taught how to subvert the prescribed uses of tools in the FAST class. This base knowledge developed by FAST is complemented by the rest of the courses in our curriculum, and students are able to learn more effectively, having already learned the tools they'll be using in those courses. When students reach their third or fourth year, they're then ready to take this knowledge and put it to work in the Biodesign Challenge, which creates real-world scenarios, putting their design skills into action. The advantage of this FAST first, Biodesign last approach is that students will be well versed in the successes and failures of design processes. They'll have increased acuity with tool use and a formative ability to unshroud complex systems. The second point we want to make about the advantages of FAST and Biodesign Challenge are that both courses are highly tethered to the real world. FAST is especially distinct from many foundation courses in that it explores through physical assignments and readings real-world scenarios that put the value of tools and the work associated with their use into a context that's applicable to students in their everyday lives. For their final assignment in the FAST course, they use their accumulated knowledge to make a tool that solves a problem they've identified on their own, and that process forces them to consider the usefulness of the things they make and the acuity of the skills they have to assess a problem, find potential solutions for it, and to use all their technological abilities to solve that problem. This assignment, where they are the customer, often results in products that are passionately ideated but roughly executed. We're not designing the course for failure here, but rather we're showing the student the necessity of iterative versions of ideas and continual research and skill building in as many areas as they have access to. This direct and emotionally charged outcome sets the students up to use their subsequent courses at the university to full effect if they are to become successful designers. By the time the students arrive at the Biodesign Challenge, they're ready to perform multiple iterations of prototypes, ask the right questions to stakeholders, and to willingly seek out helpful feedback on their designs for improvement. This is an important distinction, as the problems that students tackle in this course are the problems we all face as a society, so the stakes in a sense could not be higher. We've observed that students taking the combination of these courses are more open to feedback, ask better questions, and are more invested in what we would term good design than other students, who are sometimes more concerned with their grade or how they're progressing in the class. The final and important aspect of the combined teaching of these courses is the philosophical stance that both take towards the world and the technology we create for ourselves inside that world. The stance we're promoting is that all tools and technologies are best understood through their relationships to one another, rather than the distinctions between them. Welding is of course a tool just like CRISPR-Cas9, but is it possible for a student or a philosopher to make a stronger connection between the use, implementation, and effects of these technologies? We've seen that these students, with the completion of FAST and Biodesign, are able to see and use to their advantage the connective relations between the use of these tools. Knowing what tools to use for which problems, in which contexts, at what budget, and for a specific deadline are difficult skills to master altogether, but the systems thinking approach of courses, allied with the ability to unshroud invisible complexities, gives students a unique ability to forge a new and significant design solution for the future.